Oh. All right, actually there are more people here than I expected, given the time, but that's fine. So I trust you all saw the announcement that, in case those of you who were wondering, who were suspicious that I had scheduled this project to be due on Wednesday instead of the usual Thursday, well, now maybe you see why. So the project is due Thursday night. There will be another AutoGrader run tonight. There was one last night. So that means that I run it for a couple of hours and then turn it off. I will be running it multiple. You will probably get all the same results, or you will probably get, you may get your result. If you don't submit anything tonight, you will get the results from last time again, but with possibly updated test cases. So as we find problems in the test case set, or we add new test cases. So it is not, this is not one of these, testing is not a matter of being, quote, fair. In other words, giving you the chance to not pass a test for technical reasons. It's about finding bugs. So we do feel free to add new tests before the deadline. We won't add new tests after the deadline. So don't worry about that. Now I think I have caught up on all but one bug submit so far. If there's one that hasn't been responded to, then I'd like to know about it. Now there is a test next week. Did you decide to make an announcement about office hours or anything like that, what we were going to do about preparation for the test? Pardon me?
I have made a discussion for my session today.
Uh-huh. Okay, well, we'll get some, personally, I don't know how people feel about this in general. A lot of students like review sessions. On the other hand, a lot of TAs have this problem with review sessions that they tend to devolve into nobody has any questions, so the TA just gives some material, and that's not really very effective. So I think we're going to go the extended office hour route for this test and see how that goes. Okay, other questions, issues, what have you? Somebody asked me, I should probably, well, I can post it. Somebody asked me how you can roll back things with SVN, and I was grateful. I was happy to receive that message. And of course, the answer is, as long as you've been committing things right along, and as long as you've kept everything that's important under version control, it's relatively straightforward. So you don't ever have to lose. If you make a change that you later decide was foolish, well, you can back out of it. And that's a nice sort of thing to do. I admit it's not as easy in Subversion as it is in Git, but then what is? It seems to be equally easy to screw yourselves in either one, so I'm not sure which one to take. Okay, so let's see. We were talking. I was making some general comments or general discussion of typing last time, and so let's step back and make sure that we understand what we're talking about here. So the classical definition, as I said, is that a type is a set of values and a set of operations on those values. Now this latter thing is kind of is the modern meaning modern meaning 20 years before you were born definition, in which it's not just the data that's important in the type of an object, but it's also the things that you are defined to be able to do on that data. So, and in fact, you'll find that a lot of modern programming languages are designed with that definition in mind. So in Java, fields, instance variables, and methods correspond directly to what's meant by values and operations. Same in the class structure of Python, or C# or C++, etc., etc. Whereas in an older language like C, what you find is you've got struct, which define the data, and the operations are all separate things that you sort of associate with the data by convention or something like that. So we call all the rules that have to do with types, what types have to be used where and so forth. We call that the type system of the language. And the idea is that we are supposed to make sure what we call type checking. When you talk about type checking, you're usually talking about a static compile time activity. And the idea is to predict sort of that all executions of your program are going to do sensible things. In other words, the operations that they apply to types will be the operations that are supposed to be applied to those types. And it's sort of important to understand that, especially with the modern languages, there's a disconnect kind of between the, well, that's not quite the right way to put it. But in modern programming languages, one can have, for example, enums, that is named symbols that actually stand for integers in C and C++. And you could also have integers, and they have internally they have exactly the same representation. In fact, the assembly language instructions that you generate to manipulate them are exactly the same. And yet, a language may well distinguish these two things, especially something like Pascal, for example, will distinguish these two things. It won't let you use one in place of the other, even though they're really the same. Underneath the covers, they're really the same thing. And that's because the language is helping you, the programmer, enforce this convention that you have declared by saying these are enumerals, not integers, or these are enumerals. Is a member of an enumeration type. So it helps you to enforce that restriction, and therefore presumably make sure that your program is doing what you intend. And the example here, the example here on the slide is another one. So in C, I shouldn't say in C, but in most implementations of C, function pointers and integers have the same or similar representation. Sometimes they will be integers of different sizes, but they are at the base, as far as the assembly language is concerned, it's all the same thing. It's all some kind of integer. And I can therefore add things to function pointers, but the language actually doesn't let me. If I have int paren star f n paren semicolon, which means f is a pointer to an integer valued function, and I try to do f plus equals 1, the thing will tell me that there's something wrong. At least I think it does. It's supposed to anyway. So that's and that's because I'm almost certainly doing something wrong. Now, some of you on your project, just to bring this up, I saw a few warning messages that you might well look at. I fault myself. You might want to go into, by the way, it's not too late. You might want to go into your makefile and change the CXX flags to include this flag, this very useful G++ flag, minus wall, which means give all warnings, and this will give you the warnings that we see. So the auto grader is going to be anal about this. It's going to require you to get rid of all your warnings, which means that you fix your compilation warnings. You should always be able to get rid of those. And if you can't, then please let me know, and we'll see what's wrong with it. And also to get rid of your, you should also get rid of your horn or bison warnings. And there are these expect declarations whose purpose is to do exactly that. However, you should not use that. However, since those warnings often mean something, you should make sure that you should be careful about doing that. But the point is that you have looked at and taken care of, or at least you know about all the warnings in your program and you have dealt with them. And that is, so the reason I bring that up, because why that's germane to this, is that I've seen a number of warnings, such as, for example, one project said attempting to do arithmetic on null, which is not considered kosher in general. Even though null is actually represented internally by 0, usually in C implementations. It's even written as 0, even though it doesn't mean 0 when it's used in that context. But it's not supposed to be, it's a pointer, it's not supposed to be modified like that. So, there are these two principal uses of type, sort of summarizing. One is to detect errors, make sure that your program is consistent with your intentions for your program. So when you write the type of something, you are expressing your intentions about how it's supposed to be used, and the compiler can check that. It can also check, and this includes, this example here throws in something new, which is the differences between private and public fields, which that might also be considered a scope issue, but I think it's more of a type issue in this case. And furthermore, the other thing that you can do, it's always possible to do all of this checking at execution time, or not to do it at all. Most C implementations don't do any kind of additional checking at execution time. They try to do it all at compilation time. Java implementations do checking at both compilation and execution time. They try to minimize the latter. But the problem is that if you're going to do that, of course, you necessarily slow down your program. And if it's an operation like plus, for example, which you expect to occur an awful lot, then you can really slow things down. So as it says here, x plus y, the code must be general. So basically the code has to somehow account for the fact that in full Python, x and y can be integers, they can be strings, they can be lists, they can be tuples, they can be user-defined, they can be any type on which the user has defined an underscore add operation, or is it underscore add underscore operation. And these are all possibilities, and it somehow has to check for which one it is and yield the right result. Furthermore, if you think for a moment about the kinds of integers, if the result is an integer, then there are a couple of different representations of integers that you might produce. So it would be nice if you could represent integers as machine language integers, things that will fit in a register. But since Python can also handle arbitrarily large integers, an integer might be a big int. And just because you're adding two small integers that fit into a register together doesn't mean that the result is going to do it too. So there's just a lot of checking that has to happen, and as a result, the plus operation, without the implementation becoming clever, the plus operation can be kind of slow versus C. So again, this all gets back to this business of dynamic versus static typing. So we say static typing means, so we use these terms, I use these terms for the purposes of this class. We talk about the dynamic type of a value as being notionally, you imagine every value at runtime is stamped with a little tag that says I am an integer or I am a pointer or something like that. depending on the implementation may or may not use that information. It may or may not, this is in your head that it's stamped with this value. The implementation may or may not actually stamp it. C implementations typically don't stamp them. C++ implementations typically stamp some of them. Java implementations stamp some of them. But in your head, you can think of the dynamic type as being the label that's attached to these values that are flying around. Whereas I use the term static type, I apply that to variables and to expressions. And I say the static type is basically what the compiler knows. And it is a constraint, it is some sort of constraint, a static constraint, that is a constraint that you derive from the text of the program alone, having nothing to do with execution, on what kinds of values this container might contain or this expression might have. So, for example, if I declare an integer, if I declare a variable to be of type object in Java, I say its static type is object. That means that what the compiler knows is that X contains an object, which means it knows that it can't contain an int or a bool, those are primitives, but it can contain pointers, it can contain references. So the dynamic type that you might store in there would in fact not be object, because not in general, it might be something like string or some other, or file or something like that. So the constraint is that the compiler imposes is that the compiler doesn't know what the dynamic type that's stored into a variable of static type object is, but it does know that it is some kind of object. It is a subtype of object. So we then use the term statically typed. A statically typed language is one in which basically there are, it enforces all of these type rules. So it has a bunch of, all languages have type rules. But you call the language type safe or well typed if in fact, not well typed, it's type safe. If in fact it will catch all those errors sometime. You call it statically typed if it will catch the bulk of them at execution time, at compilation time. So there are various, this is a kind of a fuzzy definition. That's because, for a couple of reasons. First of all, you could have a language such as Bliss 10 and Bliss 11, which came to us, which were invented at Carnegie Mellon University sometime before I came there as a graduate student. This language is statically typed in the sense that it absolutely enforces every variable to have its statically known type. The problem is that there is only one type, and that's word. And it just makes sure that every variable is a word, which is totally useless. Words can be used. The operations on words include add, subtract, dereference, and all of the rest of it. So basically, the compiler tells you, yep, that's a word, all right. And any other errors that occur are, that's for the, if you dereference the constant 5, then that's just that's an error in the same category as dividing by 0. It's something that happens at runtime, and the type system has nothing to do with it. So that's not really, we don't call that statically typed. People are sort of reluctant to call C statically typed, although I would, because it's easy to do things that are never caught, like, for example, coercing an int to be a pointer to a char or something like that, whose meaning is basically undefined. Whereas Java, on the other hand, is strict. It doesn't allow you to do it. First of all, it puts a static type on everything. There are only a few cases in which it has to do any checking at execution time. It's all done by the compiler. Does anyone know of a check that has to have a type check that has to happen at execution time with Java? There are a couple of them. There's one that's visible and there's one that's invisible. We have 1, 2, yeah.
It has to check in some cases if it's the object, if it's the primitive type, and then it will quote or send in the object type, or vice versa.
But wait, well, isn't that caught at compilation time? I think that's caught in compilation time in general.
I don't know.
Yeah, that's caught. I think that you'll find that one is caught at compilation time, but there are a few that cannot be caught at compilation time. All right, what do you say? Yes, you have casting in which you say something like paren string n paren of x, where x is of type object. And that the correctness of that can't be checked until execution time. On the other hand, that's an explicit coercion. So it's a function that is supposed to, its definition is throw an exception if this is not the right type. So you might argue that, well, it might be wrong, but that's part of the definition of casting. You're supposed to be able to apply it illegally and have it throw an exception. But there is a case where where exceptions will be raised, and actually a couple of cases now with Java, now with templates, where exceptions might be raised even though you haven't written anything that says an exception might be raised here. Yeah.
Numeric, sort of implicit casting of
actually, that always has a defined result and doesn't result in any errors, I don't think. So, for example, the answer was the casting of ints to doubles. So that's now that operation is defined for all ints, I believe. But there is no implicit conversion backwards, right? So that one that's an explicit conversion, and that I think could cause problems. There is another one. Does anyone know what the array store exception is? Have you ever encountered it? Have you ever heard of it? Array store? I think that's its name. All right. There's a funny rule in Java. Basically this is a grave that the Java people dealt for themselves. So imagine that you have an array of imagine that you have an array of object. So I have array of object X. Now I am allowed to coerce I'm allowed to coerce an array of object to an array of string. I'm sorry. I got it backwards. Imagine that you have an array of strings, a string array X. And I assign this to an array of objects, which you're allowed to do. That's actually the problematic rule. You're allowed to do that. As long as string is a subtype of object, you can convert, you can coerce, or you can cast, you can automatically convert array of string to array of object. Which sounds fine, except that in something that's ostensibly an array of object, you can store anything. You can store a file, for example, into an element of an array of object. But if that array of object is really an array of strings, you're not supposed to be able to do that. And that check can only take place at execution time. So and it causes an obscure, this obscure exception to happen when that happens. Well, all right. So, fine, never mind. It's an obscure type, to be sure. Now, initially what we had was a simple rule. Namely, the dynamic type is equal to the static type. That's the rule that the compiler, that's the rule in the language, that's how it works. And that means that the language is designed so that that's true, which means that you can always tell, the compiler always knows exactly what kind of thing it's got in its hot little paws, in its hot little variables at any given time. Now, of course, that's no longer true. So nowadays, it's not that the dynamic type is equal to the static type. Let's see, do I have this in the next slide? Yes, but you can have a dynamic type being a subtype or compatible with the static type. So the typical compatibility thing you find in Java is subtype. So so this is a new notion that came about with these new object-oriented languages. So we say that the idea here is, as expressed in this sentence here, an object of type X could be used when one of type Y is acceptable. So if I'm in a context where I need an object, type object, then since strings are objects, I should be able to use a string in that context. That's the idea. So what we require is that the dynamic type of the values, we design the language so that the dynamic type of every value is a subtype of the static type of the variable that contains it, or of the expression that returns it. And the compiler enforces rules, or tries to enforce rules, to make that true. So this subtyping relation it's a relation, and it has these typical properties of orderings, namely that it's reflexive. That's the first one there. It's defined to be. It's defined by saying that if X inherits from Y, then X is a subtype of Y, and it's transitive. So if you inherit from somebody who inherits from Z, then you also are taken to be a subtype of Z. Okay. See, I think is this a reasonable point to? Right. So here's just illustrating all of this. Here's an example from Java illustrating all of these terms. So we have a class B that extends A, that extends class A. I declare a variable of type X, a variable X of type A, and I can assign a new A to it, of course, but I can also assign a new B. And in that case, X, the variable will have static type A and dynamic type, and its value will have dynamic type B. So that's basically the rule. And the rule in Java that the compiler causes this to be true, causes it to be true that everything that's put into A at all times during the execution of the program, the contents of A is a subtype of A. The contents of X has a subtype of A. It causes this to be true by simply enforcing the rule that when you assign something to X, the static types must be compatible. So so that's sort of the idea. That's basically the idea behind all of this type checking stuff. All right, at this point, let's take a brief break. If there are questions about this terminology, I think it's pretty straightforward. Good. Okay, and if you have any questions about the project, now would be a good time to ask. So when we come back.
What were the grouping tests referred to? Because we're not sure exactly what those are testing.
Yeah, I saw your question.
I think that might have been someone else's question, but at least we're not alone then.
Let me see. Let's see. Grouping testing. Group. I think it might be. Those are the expressions the association of expressions. I think. Let me see if I can get it up here. Am I on the? See, are we on the internet? I can't tell. I don't think I am. that's not what I want. I want the, oh, there it is. Ah, hang on. Huh. All right, let's see what I can find here. I need to look at here. I guess this is easy as that. Ah. CS 164 testing page 1 correct.
Well, that's probably because remember there was that issue with the out of bounds error that we weren't able to fix. So I assume that's right because it would literally compile it. It would.
Yeah, it's just a test. The grouping test makes sure that you get operator precedences correct.
Okay. Oh.
So you probably have some precedences that aren't quite right.
Okay, that's great.
Yeah.
Thanks.
Is grouping 7 the same?
I don't know. I'm not supposed to be writing your test. You're supposed to be.
Well, yeah, I have a test like that. I had a question. You said to talk to you if our bug submits didn't get a response.
Right.
I had the one where I had a dangerous trailing context or whatever.
Oh, I never saw that bug submit. I remember you showed it to me, but I didn't see the bug submit for it.
Okay.
Are you sure you bug submitted?
Yeah.
Maybe it got lost in the welter of bug submits, but I didn't see that.
I'll probably.
I was waiting for it, in fact. I remembered that you had said that.
Should I bug submit it again?
Yeah. Because that shouldn't, it's not, there is no dangerous trailing context. It refers to, there's an operator in Flex called the slash operator, and that says match anything as long as the thing after it, as long as the string after it looks like this. And it will give you that message if the string after it can be arbitrarily long. But it can't. I don't have any instances where that happens, so it sounds like some sort of an obscure bug, so send it to me. Since you can't write that, you can't produce it unless you're using Flex directly. It means that there's something weird going on, so I should know about it.
Still bug submit. I commented out the code that causes that. The thing that causes it is.
Please don't submit something. Please don't submit a bug in which you have commented out the bug.
Right.
It makes it hard to find.
I'll make the bug happen again, and then I'll find them.
Yeah.
Other thing do you have any idea what the grading rubric is as far as how many tests or what percentage of tests means what percentage grade? Because we're going to obviously try for all pass, right? But
oh, I see. You mean of our tests? Oh, I see. No, I mean it takes judgment because some of the tests are related to each other. You know, if you didn't implement the print statement, for example, you would fail almost everything, and yet it's only one error, right? So we have to be a little bit careful.
I just had a quick question. I didn't know if this was worthy of a bug submit, but I found a thing where in using octal ranges in lexical rules in Horn, if you use as one of the ends, the start or end of your range, if you use something that doesn't exactly have a representation in ASCII, like /050 or /048, it
yes. Well,
I
thought I sent back 048 is not an octal. Is not an octal escape.
I get it.
And for some reason it isn't being checked for it. I have to figure out why.
Okay.
So it interprets that as /04 8.
Okay.
Weren't you? I mean, were you the ones who submitted that?
Yes, I think that was our group.
So that was
I didn't know
that
if
was
I
the one where
remembered.
where long strings weren't working or
Yeah.
something like that. Yeah. Well, I responded to that bug submit,
I might not have
and
seen
I said just that.
Okay.
So. All right, let's get started again. So here's this notion of soundness that I was talking about before, expressed in a formal fashion. The dynamic type of E, it should say the dynamic type of the value of E is a subtype of the static type of E, the expression, or of E, the expression, and and that we add these, so we have these rules that we've just been over, and the property of subclasses that makes this work, the property of subtypes that makes this work, is that the only thing you can do, as you know from Java, for example, the only thing that you can do when you extend something is you can add methods. You can't take methods away. You cannot take methods away. You can't take fields away. You can only add attributes. So I'll use the term attribute to refer to methods and fields and anything else any other properties of the thing. So you can override a method, replace it with a new one in Java. But if you do that, then you're supposed to, but in order to override a method and not introduce a new one, you have to match up the type signature, the types of the parameters, and the type of the return type also has to be compatible in a certain sense. The term is covariant. As a result, when you get an object where you've overridden these types, or overridden something, you know that if you refer to it with the supertype, with the parent type, that any parameter checking that's done on the parent type's methods also applies to the subtype. So that means that that's what makes it valid to call an extension, a type extension, a subtype of the parent type. So we then divide the class of languages into these categories. We call the language statically typed. If the type checking occurs, generally if the type checking occurs at compilation time, that's sort of the informal definition. In order to make that possible, you've got to have a pretty rich type system. And if you've looked at the type system for Java, you've got extended classes, you have interfaces. When you get into templates, things become particularly interesting. If you've ever looked, someday when you have a few minutes or an hour or so to kill, go into the Java library, the collections class, and look at the signature of sort, and try to figure out why it is the way it is. And it uses just about every feature of Java typing, and it's a wonder to behold. I think that meditating on that alone will teach you a great deal about the type system. So then you have what we call dynamically typed languages, in which most of the type checking takes place at execution. So we have examples: Scheme, Python, JavaScript, Ruby. These are all examples of such things. And then there are the cases where untyped, they're actually typed, but they have a trivial type system like that of Bliss. So in that case, everything there are just these undifferentiated values, and there's no useful concept of a type. We don't have too many of those. Assembly language is probably the prominent example. So this has led, of course, to these so-called type wars. I was having a conversation with the editorial board of the ACMQ recently about this. It's an interesting topic. So in the 70s, sort of when I got into the field, the trend was, before the 70s, the types were used for basically to help the compiler, period. Then after the announcement of the software crisis in 1968, at the NATO software crisis conference, there was there's a move to using types for other purposes, to be expressive, to structure your programs well, and so forth. And it became the mantra that what you really want was summed up by one of our graduate students, John Foderero. Strong typing is freedom. I think that his thesis may have come out in 1984, which is what made that appropriate. So the idea that by expressing these types, you know it before you execute that things are right. The compiler is working for you to check that you're doing the right thing, et cetera, et cetera. Then along came these new scripting languages. The dynamically typed languages became popular, have become increasingly popular, and you look at some of the literature on this, and they're actually making this virtue of necessity. So there isn't any checking that happens at compilation time. It happens at execution time. And they say, well, yes, fine. So you just fold that into the rest of your unit testing, and when you execute the tests, you get the type errors. So where's the harm? And they have this concept of duck typing, as you see here. That is, this comes from that saying, as you see here: if it walks like a duck and quacks like a duck, it's a duck. So if you have an object that responds to the print method, then we could say that. Then we will just say that object is of the right type for this procedure. So it's a printer procedure. So if it prints things in some nicely formatted fashion, and if the object responds to the appropriate query, .print, then you say, okay, this is the parameter to this has to be the type of parameter to this must be the kind of parameter, the kind of value that you can say .print on. And we'll just test to see whether at runtime to see whether it does that. So there are a number of ways of using all of this stuff. So in Java, the idea is that you define sort of a generic class of operations without giving the specifics, so that you can have different choices, and you can have methods that will work for anything as long as they have the right operations. So in effect, what's happening is from the bad old days of really, really, really strong static typing, where the dynamic type had to be equal to the static type, we say, well, we'll back off on this. We'll let you pass in things that have different types, just so long as they all conform to this interface. All right, now we get into a slightly different topic that's related to typing, and that's the idea of coercion or conversions. So I first encountered the word coercion in this context, in the context of Algol 68, which basically is what turned people off to coercion, I think, because it had an extremely rich system of converting things from one type to another, and it had a large number of a fairly large menu of coercions. Oh dear, it's March, isn't it? And it's Wednesday. Okay, and that means it's the end of class. Okay, so we'll stop here.